moves through the system. At their heart, all simple harmonic oscillators are about energy. And there are quite literally three major types of harmonic oscillators. There's the ideal system, which is what we're going to talk about here. There's damped harmonic oscillators. And I'm not going to write these words down because I'm starting late. You should write them down. There are damped harmonic oscillators where they're losing energy all the time. Damped harmonic oscillators. And then there's driven harmonic oscillators that receive energy from the outside to make sure they continue to operate. So we have ideal, we have damped, and we have driven. You're familiar with all of them. The simplest idea for you to understand would be to think right to what you did in the lab, where when you started the pendulum at the beginning, it didn't stay going. Right? After a few minutes, it stopped. That's a damped system. Now, if you've ever been on a swing, you're familiar with a damped harmonic oscillator. You being on the swing, you were on a system that was losing energy the whole time. When you were just a little baby, somebody put you on the spring, they pushed you. They created a driven system. In a driven system, you're receiving energy from the outside to maintain your oscillation. When you figured it out, little kids take a little time to do this, but when you figured it out, you no longer needed somebody to push. You could pump the swing yourself. You figured out if you wobbled just right and flapped your legs just correctly, you could create or add energy to the system so that you would be able to maintain your oscillation. That is a driven system. You provided the external energy to drive the system. So I started on Friday talking to you guys about the difference between having a system that was using a restoring force and one in which there wasn't a restoring force. And I talked about the necessity of that negative sign in Hooke's law. Remember all that? Well, we're going to go through these stages of a simple harmonic oscillator, and then we're going to take a look at a system I've set up for us. But to do this correctly, I want to identify first the equilibrium position, which is exactly what we were talking about right at the beginning of class, or right at the end of class on Friday. The idea that there is a equilibrium position. The equilibrium position in the relaxed state, the object just sits there. But it also represents the point at which the spring has not been pulled out or pushed in. Now, you should probably put in your notes someplace that we use the spring as the ideal system. But all oscillators that have a restoring force behave like the spring. So the spring is our ideal system. But don't assume that every system has a spring. If you know that it's a harmonic oscillator, then it will behave like the spring system behaves. So, first thing we do is we pull the object out. This initial displacement is called the amplitude. The initial displacement is called the amplitude. It is us establishing the energy of the system. Because at this moment, we have placed potential energy in the system. Right? We pulled the spring out, and therefore we have potential energy due to 1/2 kx squared. Now, I say x, but I'm going to put x max there. The word max, really little, next to x, to remind me that this represents the maximum amount of potential energy. The object's not going to ever be this far out again. It won't go any further than this. It might make it just back to this point, but it'll never get further away than this, because we are establishing how much energy the system has. Now, at this moment, we're talking like this is t equals 0. We're about to release the block. The block is experiencing a single huge force this way. And that force is at a maximum because the spring is pulled out the most right now. And we'll remember F equals minus kx. So if this is at its maximum, then the force is at its maximum. And if the force is at its maximum, the acceleration is also at its maximum. But that at this instant, the velocity is 0. It's the instant we let it go and it begins to move. So at that instant, the velocity is 0. There hasn't been any time for the spring to cause the object to move. Now, you don't understand this yet, but the problems are going to refer to these positions by their energy, their force, their acceleration, or their velocity. They'll say the object is at the position where the velocity is 0. And you'll need to know that at that moment, all of these things are true. So when I say that the oscillator is at the position where the velocity is 0, I'm also telling you it's at its maximum displacement. I'm also telling you it has the maximum amount of potential energy. I'm also telling you that it's experiencing the largest force and the largest acceleration. When they indicate one of these positions, you need to know that all of these other things are true. That's how they're going to treat them on multiple choice. And the very first question I asked about this in first period, they got it wrong. And the very second question, they got wrong too. So I'm warning you ahead of time. This is what they're going to do. They're going to refer to these positions based on one of these properties. A moment later, the object has moved so that it is not as far away as it was before. It's at some middle position, x, which means it has some elastic potential energy because it's still not back to equilibrium. But now the object is moving, so it has some velocity, which means it also has some kinetic energy because it's moving now. So it has kinetic energy. Moreover, the force has now been diminished. The spring is not as far pulled back as it was, so there's less force. And because there's less force, there's less acceleration, so the acceleration is also getting smaller. So it starts with maximum acceleration, and the acceleration doesn't stay the same. That's going to be important. That means that there's no motion equation that we currently have that can describe this motion. Our motion equations are all based on an acceleration that is constant, and this acceleration is changing. So you can't use any of the Galilean motion equations here. They don't describe the motion at all. Now, at this midpoint, this middle position here, the object is increasing its speed all the time, but the acceleration is getting smaller all the time. That's going to be one of those things where you'll get it wrong on the test, and I look forward to that. But during this time, as it approaches equilibrium, the velocity is getting bigger, but the force and acceleration are getting smaller. Energy is moving from elastic to kinetic. And eventually, the object will finally make it back to the equilibrium position. So let's talk about the equilibrium position. Keep bringing these all the way to the top so that people can see them. There. So, at the equilibrium position, the force is 0. F equals kx, x is 0, so force is 0. Also, that means the acceleration is 0. We're all the way back at equilibrium. So, acceleration is 0. But velocity is a max. It's at the fastest it's going to travel. That also means kinetic energy is at a max. but the net force is 0. It's not experiencing any force at this moment. So nothing's pushing on it as it passes right through equilibrium. Also, this is 1/4 of its motion. So the time is 1/4 of the period. So this occurs at the quarter period mark. Now, I don't think this is like a huge surprise or anything, but we'll continue this just for a little bit longer, realizing that the moment it passes, the force suddenly begins pushing in the opposite direction. The object's still traveling with a velocity in this direction. It's still moving to the left, but the force has now moved to the right, and that means the acceleration is also to the right. So it is slowing down, but still traveling to the left. That also means that at this moment, we've got a combination of elastic potential energy and kinetic energy. We have both, because we started to compress the spring now, but at the same time, we are moving, so we have kinetic energy. It's the inertia that's keeping this thing going. Eventually, we'll come to rest again. We'll come to a point where the object will finally be stopped. The force has been increasing in this direction. The force will reach a maximum, because it's at this moment where it stops, maximum compression of the spring. The acceleration, also a maximum, because the force is a maximum, but the velocity is 0. Right, we're stopped. So this means all of the energy is elastic potential. We have made it to the other side. And we will be the same distance on the other side as we were at the start. The object is symmetrical, so it will oscillate the same on both sides. Now at this moment, although the velocity is 0, the force is at a maximum. So this object is accelerating at its greatest moment when it stopped. You understand how much you're going to get that kind of stuff wrong. When the acceleration is 0, it's at its fastest velocity. And when the velocity is 0, it's at its maximum acceleration. It doesn't behave the way you think it is. And you'll get these multiple choice questions wrong. Little charts with force max, acceleration max, V max, and you need to figure out what's what. Also, this point, the time is 1/2 of the period. We have done 1/2 of the motion. This is not a full oscillation. All of this represents just 1/2 of an oscillation. I'm not going to go back and talk about the return trip. You can do the return trip. It's the same. But remember, this is an oscillator. If there's nothing taking energy away from the system, then the total energy of the system is whatever you gave it at the beginning. You establish how much energy it's going to have. And energy is conserved. So at any point that we're looking at the object, at the top it's 1/2 k x max squared. Then it's a combination of 1/2 kx squared plus 1/2 mv squared. Then at equilibrium it's 1/2 mv max squared. Then it's a combination again, 1/2 kx squared plus 1/2 mv squared. And then finally, it's all back to elastic. If no energy is lost, all of these states are equal. If no energy is lost, all of those states are equal. Now, I want to show you something, and You guys are smart cookies, so you'll probably be able to catch on to this. So I'm going to go to a new screen here for just a minute. There was an initial amount of energy at the beginning. After a few moments, all of that energy was turned into kinetic. Now, I'm just going to solve this for the maximum speed. And I want you to see what kind of happens. Actually, I'm going to solve this for the maximum position. First, I get rid of the 1/2 and divide both sides by k. Just going to do a little algebra. That gives me x max squared equals m over k times v max squared. Okay, so far? Take the square root of both sides. Does something in there look familiar to you? If you have your lab write-up, something in there should look familiar to you. You see it? Keep a watch for this. This ratio is important for this discussion, and it's going to come up a couple times. To see it, I have to show you something else, and I'm going to switch over to show you something else, but it's going to be a second because I have to get something connected over there. I have to connect to the car. Now, I'm going to turn the lights on and stuff. I'll make sure the car is on. Let's see. It appears to be okay. I want 2 graphs, and I want this one to be position, not force. I want this one to be velocity. All right, so we're going to look at collecting data. I have a new car. I was going to get these for everybody, but they're $300 a piece, which wouldn't be terrible, but I think they'll get abused like the ones I already have, these. That somebody will borrow them and they'll come back abused. They're kind of neat though because they've got the magnet things. I can flip them around and have the magnet side out, or not have the magnet side out. But they've also got a sensor at the bottom, which means I don't have to use the motion sensors that's built into the car. It's also got an accelerometer for all 3 axes. It actually can do quite a bit, but I know if I buy one for each table, which 8 times 300 is a lot, somebody will borrow them and they'll come back all wrecked. And I can't bring myself to do it, so I've ordered one. You might want to stop watch. So I'm going to set this into motion. But what I'm going to do is I'm going to pull it back farther than I should, so I have time to walk over there. This first one's going to be bad because it's going to crash into the top. And then it'll come back down. When it comes back down to its maximum position, that's when you guys should start your stopwatches, okay? Ready to follow along? So here we go. All right, so I've collected a little data. And I'm hoping you can see the data just fine. So although I've collected a little data, it looks like all that setup, which was for the stuff I really wanted to do, we didn't get to at all. That's disappointing. So tomorrow we'll do this, and then we will talk about the computer stuff. So if you have a tablet or you have a computer and you want to learn the Excel thing, tomorrow would be the right day.